In this video I want to consider another form of expressing vectors, and that's polar form. So we've already considered component form. Now our second form is polar form. And a vector can be expressed in polar form as u is equal to, and the two parts of polar form will be r and theta, two parameters here. R is the magnitude of the vector, and theta is the direction. And the direction is measured anti-clockwise from the positive I direction. So if we say positive I is in this direction here, then we're measuring anti-clockwise from that, which is sort of what we do with a lot of things, isn't it? We have our four quadrants. We start at the positive X direction and measure through quadrant 1, 2, 3, and 4 in that direction there. Let's think of a couple of examples to try and demonstrate r and theta. So first of all, if I had a vector A whose magnitude was 13 and whose direction was 120, well, the first thing I need to do is get my direction. So if I started from the positive I direction and then measured round 120 degrees anti-clockwise, then my vector would be pointing up in that direction there, and it would need to have a magnitude of 13, so the length of that would need to be 13. Alright, what about a second one? Magnitude 18, direction negative 25, so negative 25 is going to actually be measured clockwise because it's going to be the opposite direction to anti-clockwise. So thinking of that first, there's my positive horizontal direction. I'm going 25 degrees negative to anti-clockwise. So there's the direction that B needs to point in, and it needs to have a magnitude or a length of 18. So how do we go about converting between polar form and component form? Converting between our two forms, and we could need to go either way, and we will at different times. So let's think about a vector u here, which has a magnitude of r and a direction of theta from the positive I direction, or the positive horizontal. And let's say its horizontal component was x units and its vertical component was y units. So the two ways that we could express that would be as xi plus yj, which is the component form, or as r theta, which is polar form. So how do we go about converting between those? If we knew x and y, how do we find r and theta? If we were given it in this form, how do we change it into that form there? A bit of trigonometry is going to help us. So first of all, in this triangle here, we can see that cos theta is adjacent over hypotenuse. So cos of angle theta is x over r. And if we simply rearrange that to get x, we can get that x is equal to r cos theta. So given r and theta, I could find x by multiplying r times cos theta. And that works regardless of the magnitude of theta, whether it's an acute angle or it's in quadrant 2, 3, or 4, it doesn't matter. If we rearranged sine theta, we could get a result for y, that y is equal to r sine theta. So we can easily find x and y if we know r and theta. How about working the other way? Well, we've already said that we can get the magnitude of a vector by just using Pythagoras theorem. So the magnitude here is going to be equal to the square root of x squared plus y squared. And to find theta, we could use our tan relationship. So tan of the angle here is going to be the opposite over the adjacent. Now, one little note to that, and we'll see it in an example that we do, that we just need to take careful note of the quadrant that theta lies in. Because, for example, if y and x gave us a positive number, then finding tan theta using our calculator would give us an angle in quadrant 1. But remember, this could be positive if y and x were both negative. And if y and x were both negative, so negative y or negative x, negative y would actually mean that the vector was down in quadrant 3. So we will need to think about that. And like I say, I'll try and show you that with an example. So those are our two sort of ways of converting. You'll find some of that on the formula sheet to help us. So we need to be able to sort of apply those. So let's grab a couple of examples, starting off with a conversion from polar form to component form. So here we've got a vector expressed in polar form with a magnitude of 12, a direction of 150, and we want to express it in component form. This is probably the easier way to convert. So we can just sort of sub straight into these results here. So we can say, and we could write it sort of straight in component form if we wanted. So we can say now x is equal to r cos theta. So that's going to be 12 times cos 150, and y is going to be 12 times sine 150. So therefore, vector u in component form, well, 12 times cos 150, so cos 150, which is the same as, well, it's 30 degrees from the horizontal axis, isn't it? So it's going to be a root 3, let me just move that a little bit, root 3 over 2, but it's going to be negative because we're in quadrant 2, where cos is negative. And 12 times sine 150, well, sine 150 is a half. So we really need to know our exact values here. So what's that? Negative 6 root 3 and 6. And we could write that as, negative 6 root 3i plus 6j. But one of the things I want you to notice here is that as long as we just sub correctly into those results, these ones down here, then the maths will correctly give us positive and negative components. If you think about what the vector 12 and 150 looks like, it looks, no, not that steep, is it? It's more like kind of that there. Okay, so the angle's 150 degrees. So we know from that that the I component is going to be negative and the J component's going to be positive, and we can see that in our answer. It's always worth checking though, because if that wasn't negative and that positive, then we would have done something wrong in our maths. So think about where this vector is. In this case, it's in quadrant 2, and check that your result makes sense of that it actually does have a negative I and a positive J component. Alright, let's do a second example. So this time express in polar form the vector which in component form is 8, negative 8 root 3. Now I think it's always worth drawing these, and even for example 1 I could have made a sketch there, but particularly when you're going from component form to polar form. So I want you to think about where you would sort of be in what quadrant. So if we were going 8 and negative 8 root 3, our vector would be something like this. So that would be 8, and this here would be 8 root 3. So our vector would sort of be pointing down from the origin into quadrant 4 if we were to plot it as a position vector from the origin. So there's the r that we want to find, and there's the theta that we want to calculate. So r is going to be equal to the square root of 8 squared plus 8 root 3 squared. Now you can write that as negative 8 root 3 if you want, but when you square it, it's going to become positive regardless. So what are we going to have there? 64 and then 64 times 3. So that is going to be, what's that, the square root of, what, 216 is? It's going to work out as just when we take its square root, it's going to be 16. So its magnitude there, or its length, is 16. And we've also got that tan theta is equal to 8 root 3 over 8. So what I would be doing, whichever quadrant you are in, I'd just deal with the triangle you've got. So here I've said tan theta equals y over x. So you might say, well, why aren't you putting negative 8 root 3 over 8? Well, all I'm doing is in this particular triangle, I'm working out the value of theta. If I'd been down in this quadrant here, I would have been working out the value of theta in that triangle. And then I would be saying, how do I express the angle all the way from the positive I direction? Okay, so if I found an angle down here was, 60 degrees or 30 degrees, I'd be saying, well, the direction is 180 plus 30 or 180 plus 60. Here I'm just going to calculate what theta is, and then I'm going to express it as a negative direction. Or I could express it as 360 minus that value there. Alright, so that's theta, or tan theta, and so therefore theta is going to be equal to the inverse tan, and this one's just of root 3. It simplifies too, doesn't it? So inverse tan of root 3 is equal to 60. So therefore, I can say, well, my vector v in polar form, it has a magnitude of 16, and it has a direction of negative 60. Or I could say v is equal to magnitude 16 and direction positive 300. Both of those would be perfectly fine.